Hello. Hey, Archer. How are you guys? Nice. How was the senior assembly?
Boring.
Right. Yeah, it's usually the case with assemblies. Was it all over Zoom?
Yeah.
I see. And they don't let you guys chat, right? On the it's all
They
over.
did, but then it kind of got out of hand, so they had like shut down the chat.
Oh, that's pretty funny. How many people all like joined that meeting?
Out of like the 214 seniors, only like 120 joined.
Oh, that's not bad.
Yeah.
Yeah, if there's a chat with 120 people is gonna get out of hand. That's pretty funny. Um, let's see. Uh, New participants on entry. Okay. Just share my screen. I learned a fun game from my fifth grade class this weekend, and if we have time, we can play. I'll show it to you guys. We can play later. Still haven't figured out exactly the optimal strategy, but it's similar to tic-tac-toe. But maybe we'll take a break like halfway through, and we can check out this game. I'm going to share my screen. Okay. All right, everyone. Good afternoon. Welcome back. I got an email over the weekend. The student asked a good question about like midterms and stuff like that. So in this class, the exams are just kind of like count the same as midterms. We don't really have one big midterm. We'll just have several different exams. We'll have about like I think maybe 4 exams total, maybe 5. I have to look to find out exactly, but uh, we'll have like 4 or 5 exams and then 1 final. And the thing about the class is the schedule is a little bit different than the high school. So our semester actually ends at the towards the end of like late January. So we'll have our final like maybe January, sometime after January 15th. And I think we'll do most of the exams will be done before winter break, and then or maybe we'll have one more exam in January, and then the final will be sort of a cumulative test with maybe more weighting towards the second part of the class. And there'll be one part of the course which is like I think the last part of chapter 8 that we'll just have one exam and it won't show up on the final. Okay, so I want to continue where we left off last time. So last time, if you guys remember, so today I want to go over continuing with systems of linear equations. I want to talk about when solutions exist and when they don't, and how to understand the geometry behind it. And then maybe we can go over the homework and start getting into some word problems. That'll be the goal for today. So this is linear system of equations. So 2 by 2, because there's 2 equations and 2 unknowns. So last time we saw we could use the method of elimination and substitution are 2 excellent algebraic methods. They're really like algorithms because they give you a step-by-step process for solving the system of equations. But alternative, and this is going to be a little bit of a quick rehash of what we did. I think a lot of you had to leave, so this might be a repeat of what some of you saw at the end of last class. So if you have a system like, let's say, which one did we have earlier? Well, let's come up with a new one. Say y plus 3x equals 5, and 2y minus x equals 1. Oh, sorry. So, does anyone remember, and you can message me in chat or just raise your hand, what's the type of format these equations are in? What's the term for this? What's this called?
Standard form.
Awesome. Exactly. It's a standard form. Personally, like, message me, hit yes if you like, if you would use elimination here, or hit thumbs up if you would use substitution. So just to kind of see where people, which method people like more. Nice. And there's no right answer. This is, I guess when it's in standard form, you generally want to use elimination, but you're welcome to use any approach that you're comfortable with. Yeah, so I would probably use elimination here as well. And we could solve it that way. Now, an interesting idea, though, is to actually convert, these are both equations of lines. This is an equation of line. If you convert each of them into an equation of the line, you make an important observation that what you're really looking for when you're solving a system is, so I'm going to add in the x and divide by 2. So I'm just going to write it here, y equals negative x all over 2 plus 3 over 2. So these are two standard equations of lines. And another approach we can take is to find a set of solutions that simultaneously solve both. What you're really looking for is a point where the two lines cross. So I'm going to try to graph this. I'm going to scroll up here, and I'm going to change the paper. No, I'm going to change this paper so that it's a little bit like graph paper. And I'm just going to try to graph it. So let me make this a little bit larger so I can make my axes. That's a little too large. I'm going to graph this one here, and I'm going to graph this one. Okay. So we have our XY axis. And this is actually pretty nice to do on one of these note-taking apps because they have the straightening feature, so we can draw lines pretty well. Can anyone tell me, how do I, what's the slope and intercept of the first line?
Y-intercept 5 and then slope 3 over 1, negative 3 over 1.
Excellent. So it's starting up at 0, 5. So starting at 5 points on the y-axis. So was it 1, 2, 3, 4, 5 right here. And it's going down 3 steps each time it goes 1 to the right. So it goes like that. And like that. Okay. And now I'm going to graph this one maybe in purple. Let's see how good I can do this. Don't love that one. Let me erase that. That's terrible. Try again. 3, 1. That's better. It's time for so that's the purple line here. And is everyone comfortable? And jump in if you're not. How I did the, oh, sorry, I made a mistake here. Or does anyone see my mistake for the second equation? I want to catch the mistake on the board. For the second, nice. Allison, very good. Yeah, I should have added. I subtracted. I misread that minus sign there. So this should be a plus. So I want to add the x, and then divide everything on the right side or on both sides by 2. And I'll be left with something that starts at 3/2, so that's 1.5, and it moves up a half. So that's over here, and the slope is 1/2, so it's not super steep. So it goes over 1, up 1, up a half, over 1, up another half. So what you can see is it's going to move like that. Okay. So can anyone tell me where the point is that they cross? What would be the coordinates?
1, 2.
Perfect. Nice. So this would be at 1, 2. The intersection. Maybe I'll make it a red point. And if we check for x equals 1 and y equals 2, and we plug in each point into the equation, because it lies on both of the lines, it has to satisfy each of the equations. Therefore, it's a solution to the simultaneous system of equations. Or we just call it the linear system of equations. Okay, please hit yes if you're comfortable with what we just did. And please hit no if you have any other questions or have something you want to ask. And don't hesitate to ask. This is a really important idea. So I got 7 yeses, 8. Let's see if we can get it to 15. So everyone, awesome. We're at 12, 13, 14. And some no's are okay as well. If anybody has any, like, I'm happy to go over anything. Awesome. Okay, great. So, yes. So the x over 2, so once we ask a good question, how does the x over 2 like give us that slope? Because this is really, x over 2 is a fancy way of writing, or just another way of writing 1/2 times x plus 3/2. That number in front becomes 1/2. There. So what we see here is that when we have 2 lines or a system of equation, we see that we're usually going to get a crossing. In most cases, those are going to be a solution. Can someone who didn't hear the solution last time before the assembly, can someone suggest a situation where you might encounter a set of 2 lines that don't have a solution or don't have an intersection point? So what kind of scenario could there be where you come up with a system of equations, but there's no solution? and think about this kind of picture and see what kind of picture can you draw where there won't be any solution. Nice, Archer, very good. A pair of parallel lines. So if instead I wrote my set of equations was, let's just do another pair. If I wrote this, let's just actually try to solve it. Y plus 3x is equal to 5, and y plus 3x is equal to 7. Actually, let me give you another one. So let me do 2y plus 6x is equal to what? Okay, so I'll give you guys a few minutes here. Please try to solve this system of equations using elimination. Or if you want to use any other method, you can, but I would recommend using elimination. I'll give you guys a few minutes to do this. Nice, Gabrielle. And so what does that leave you with? And message me when you kind of run into a roadblock. And hit the yes button also when you're done trying to solve it. And if you're stuck where to begin, also message me. I'll give you a little pointer. And what I like to, when I do elimination, I'm pretty flexible, like whether I'm going to subtract the equations or add them or multiply by a positive number or negative number. Generally, I like to just make my life as easy as possible, and I like to avoid multiplying by negatives because I'm always afraid I'm going to do something wrong. So yeah, I generally, when I think of combining the equations, I'm not thinking about adding or subtracting. I'm just thinking about doing the right operation that will cancel out the terms that I want to be canceled out. Okay. Any volunteers? Let me see here. Any volunteers want to explain what they did? Kanjit, go ahead. Tell us kind of how you approached it.
So what I did was multiply -2 to the first equation. So
Okay.
then I got -2y minus 6x and then equals -10. And then to cancel out the y's and then you cancel out the 6's and then left and then cancel. You did 10 minus 12, so 2.
Nice. And so what do you get 2 on the right side, and what's weird, what do you get on the left side?
Nothing.
You get 0. So somehow this doesn't make any sense. So Kanjit, what can we conclude from this? What can we say about the solution to this system?
It's not a line.
It's a line.
Not linear, it's hard.
What was it? So it's it's linear because if we rewrite both of these, we'll do this in a second. So rewrite each equation. Whoops. Try to rewrite each equation in slope-intercept form and see what you get. So if we rewrite the first equation, we get y is equal to minus 3x plus 5. That's just subtracting, subtracting the 3x. Can anyone tell me what you get in the second, if you rewrite the second equation in y equals mx plus b form? So not standard form, but mx plus b form? Nice. Nice, Lily. Nice. Could you? Yeah, you get the very similar expression. So they're both totally okay equations of line, but what's the observation? What do we know without necessarily drawing them? Without necessarily drawing them, what do we know? Archer, perfect.
Parallel?
They're parallel. Yes, exactly. They have the same slope, so they both have slope -3. Therefore, they're parallel. But what do they have different? They have different as an intercept, so they're going along the same direction, but they never touch. So this is 2 ways of showing that this system is inconsistent. Consistent. And it's a really fancy way of saying there's no solution. And over here, we can see that the lines are parallel. Have the same slope, but different intercepts. So they never intersect. Because they are parallel. Awesome. Any questions on what it means for and what it means for system of equations to have no solution? So you can arrive at that in 2 different ways, and it's always nice to make sure that you understand the geometry behind it as well. That the fact that can only happen if 2 lines are parallel. By the way, a quick observation. Can anyone come up with a trick to tell if 2 lines are parallel when you just look at the standard form without doing all the work to convert it to mx plus v form? Because obviously we know if they have the same slope that they're parallel. But is there any way, just from looking at the on the left side, what's like a shortcut we can do to check that they have the same slope? Anyone have any ideas? Nice, Gabrielle. You want to share that idea?
Sure. They're all multiples of each other, like just by looking at it.
Yeah. So? Can you be a little more specific? That's very good.
Like 2 and 3 makes 6, and then 6 divided by 3 makes 2. So if you were to use the y to like cancel out and you do -2, it's just gonna add up. Everything's gonna add up.
Nice. So yes, Arch also good idea. It's factorable. So the observation is that they're all multiples of each other, that the coefficients are in direct proportion. So y, the coefficient of y in the first equation is 1. In the second equation, it's 2. So there's a ratio of 2 to 1. For the x's, the coefficients are in ratio of 6 to 3, which is also the same as 2 to 1. And you can also look at it like, it's a lot like similar triangles. So 1 to 3 or 2 to 6 is another way you can look at it. So let me put it here. And this is not that surprising, because to find the slope, you move one of the x term over, and then you divide by whatever number's in front of the y term. So you're always, to find the slope, you're just taking the ratio of the coefficients. So if they're in the same proportion, that ratio is not going to change. So there's nothing that interesting with the shortcut, but it's just something good to be aware of. So you can check if equations are parallel by comparing the ratios of the coefficients. And there's a few ways to go about it. Here I said 2 to 1 is equal to 6 to 3. And in particular, we can see that they're not parallel because, that they're parallel because the intercept, here's a really important question, and we're going to do a few of these for practice. Could anyone volunteer, what would, well, yeah, let's do one similar example now. So I'm going to just change something up here. So now we saw that an example of two lines that they cross at a point. We saw an example of two lines that they cross nowhere. Can anyone volunteer to explain what's a third possibility if you have two equations? So they cross one point, they cross nowhere. What else can happen possibly? So what other ways can two lines intersect? You just have two random lines. And it's kind of like a tricky answer. But anyone have any ideas? Anyone from last class who heard the answer, you're welcome to also, if you remember. What's the third way that two lines can intersect?
If they're the same line.
Awesome, exactly. Yeah. If they're the same line, then you'll have an infinite number of solutions. So let me just copy and paste this example here. This is this is called infinite solutions. So everything is the same, but instead of 12, imagine I use the number 10. Do you guys see what would happen if I tried to do elimination? I can change the first equation to become minus 2y minus 6x equals minus 10, and I add them, combine them together, I get 0 equals 0. And if you convert these to intercept form, you get exactly the same equation, y equals minus 3x plus 5, and this one also becomes 2y equals negative 6x plus 10, which if you divide everything by 2, you can just write it as y equals minus 3x plus 5. So these are the same line. So when all the coefficients and the constant term are in the same proportion, so if you look at the coefficients here, just highlight them. The coefficient here, I'm not writing it, but it's, you know that there's a 1 here. 1 to 2, 3 to 6, 5 to 10. These are all in the ratio of, 1 to 2, or 2 to 1, however you want to set it up. But so when everything is in the exact same proportion, that tells us that it's exactly one equation is just the multiple of another equation. And when you take an equation and you multiply the entire thing by just the constant, the entire equation, you're not changing the substance of the equation. So any point that satisfied the equation before will still satisfy the new equation. So you're not changing the geometry, you're just changing what it looks like. And there's a lot of examples like this in math where you change what something looks like, but you're not actually changing the object. Can you guys give me one example of something like that in another part of math, where you change what it looks like, but you don't actually change the thing itself? So factoring and fractions, exactly, are both very good ideas. Simplifying fractions, exactly. So finding the common factors in the numerator and denominator and simplifying them, you make the number look different, but it's really the same thing. So the same idea applies to equations. And we call this a set of, whenever you get 0 equals 0, so before we got 0 equals 2, which it's called inconsistent, that means there's no solution. Whenever you do elimination, you get 0 equals 0, it means that the system is indeterminate. Which means you can't find the unique answer, which means that it's a fancy way of saying it's an infinite number of solutions. There's not just one solution, but there's a lot of them, because basically the solution is the entire line itself. Okay. How do you guys feel about these examples and these kind of 3 ways that you can end up with a solution to a linear system? So hit yes if you feel pretty comfortable with everything that we just went over, and please hit no if you have any questions, or message me any questions also. And it's really, honestly, very, very simple, right? Like if you just thought about, like, without any algebra, I just said to you, how many ways can 2 lines intersect? Well, obviously, straight lines can either cross once, they can never cross, or they can be directly on top of each other. That's the whole idea here. There's nothing deeper than that. If you understand that, you can answer somewhat more confusing looking questions rather than to just solve like a system. You can answer slightly more abstract questions that will test your understanding of, like, how does this system need to look like in order to have a certain number of solutions, which is a sort of deeper level of thinking, which is, it's not that it's very difficult, but it requires you to just be comfortable understanding these idea of like connecting what the equations look like and them being parallel with like how many solutions there's going to be. So let's jump into an example like that. So and I like these examples. They used to be on they are on the SAT, but I don't know if you guys are going to be taking that anymore, so it's not super helpful. But I still think it's a good concept to be aware of. And after we do maybe 2 of these problems, I'll show you guys the game that I saw over the weekend in my 5th grade class, which I thought was pretty fun. Okay, let me go back to, let me change the normal paper here to this one. Let's go back to, okay. So, so for which constants A, B, with the following system have no solution? So let's say we have AX plus 1 is equal to A, and 3x Okay, so this is a type of problem that would show up on the SAT, and it's one that I like to ask on the midterms. And if you know how to approach it, it actually is much simpler than it seems, because it seems a little bit abstract. But here's the question. For which constants A and B, so A and B we're thinking as parts of an equation. They're not like variables in the traditional way that we think of them. But we're trying to find values of A and B so that the system has no solution. So I'll give you guys a little bit of time to think about it. If anyone has any ideas, please message me. And if anyone's totally stuck and needs a little hint, you can also message me. I'll write you back if you need a little hint. All right, so far we got a few good solutions and a few people who are kind of thinking about where to start. So keep thinking about it. I'll give you guys a little bit more time. Those of you who were not sure where to start, see if you can kind of apply what we just learned about what it means for there to be no solution. We learned that there's something important that needs to happen for there to be no solution, and see if you can quantify uh, what needs to happen there. I'm really happy to see that some students are, don't know the answer, but you're trying to come up with it on your own. That's really what math is about. It's not about me just telling you, hey, I'm going to show you how this problem is done, and then you just copy it. Really try to figure out kind of how do you apply what we just learned. What does that mean in this context? And I know that everyone can do it. So I'd like to hear from at least maybe 6 more students. So if you haven't messaged me, please message me either the answer that you got or that you're just stuck and maybe the answer that you think is right. And if you're not sure kind of what your approach was. I really want to hear from you guys. So at least 6 more students and then we'll go over. Okay, so thank you guys for responding. I'm going to give a nice hint here. Uh, so and someone Yeah, I'll give a hint and then give you guys a little bit more time uh, uh, um, to think about it. So we just learned that in order for there to be no solution, the equations have to be parallel. So how could we set it up so that the equations are parallel? And if you remember what I mentioned last time, there's kind of like a shortcut when when the equations are in standard form. Rather than just look at the slope, you can look at the coefficients. So that's a really good starting point, is saying, okay, we want the equations to be parallel. So we want to know something about the slope, and we want to figure out something about uh, the intercepts. But focus first on the slopes and the coefficients of x and y. That's kind of a really important idea. So those of you who messaged me that you were not sure, I'll give you a little bit more time to think about it, and message me if that hint helps you a little bit. So maybe first focus on figuring out what should B be. Okay, let me ask here. So any more solutions? Archer, go ahead. That's just tell us what you got and how you were thinking about it.
Just realized I was muted. So for the A, it wouldn't really matter all that much what it was, because all it will act as will be the what's it called, the B, the and the M, the Y intercept,
Nice.
and then the B just would have to be uh in a similar ratio to that of 2 to 3. So for the 2 to B, it would have to, it's a would be a times 1.5, so then it would equal 15.
Excellent. Yeah, maybe let me rewrite this. So you can do proportion any way you like. I'm going to do it the way that Archer says. So 3 to 2 has to be equal to b to 10. This is the observation we noted. In order for the slopes to be the same, the ratio of the coefficients has to be the same. So these aren't officially the slopes, but it's just we're just taking a proportion, so that we know that this has to happen. When you solve this, it's exactly like Archer said. You get 1.5, which is 3 halves, times 10, which is 15. So this makes the lines have the same slope. And Archer, please continue. So you had a good idea. What about the A? How do we now that they have the same slope, what do we need to make sure about the A?
Sorry, what was your question? I was keeping readjusting my computer.
Oh, no problem. I was just asking, so now that we know that b equals 15 makes them parallel, if we don't want to have any solution, what do we need to make sure about A?
We need to make sure that A doesn't equal 40, so that it fits with the ratio rule.
Excellent. Perfect. So if A was 40, which would also be in the ratio of 3 to 2, or however you want it, like if 2 to 3 equals A to 60, which would imply that if A equals 40, then the lines, then we know that everything is in the same proportion. The lines are identical. So if we offset A to be anything not equal to 40, if A is not equal to 40, then they are offset. They have different different intercepts. If A is not equal to 40, they have different intercepts, and therefore there'll be no solutions. So the answer to this problem would be B is equal to 15, and A just be anything not 40. You can do A is equal to like 39, A is equal to -2, whatever number you want. The general answer is just A is anything that's not 40. Okay, please hit yes if this explanation makes sense, especially if you were a little bit thrown off in the beginning about like where are all these letters coming from, what do they all mean? So I only see 6 people saying yes or no. I'd like to see at least 5 more people. Awesome. So a few students, I see a few students who said they're still a little bit lost. Please message me if you feel a little bit unsure, like which step you feel unsure about, or you can just welcome to hit unmute yourself and ask. And we'll do one more example, and then well, actually, yeah. Why did you divide 3 over 2? So that's a very good question. So one student asked, why did I do 3 over 2? So all I'm doing is I'm setting up a proportion 3 to 2 and 10 to b. And you know when you have a proportion, it doesn't matter what's on the numerator and um, it doesn't matter what you put on the numerator denominator as long as you're consistent. So I just wrote 3 to 2 equals b to 10. That's like if the coefficients from the second equation have to match up the coefficients of the first equation. On for the solving for a, I did it the other way. I did 2 to 3 is a to 60. You could have also just done 3 to 2 is equal to 60 to a. And then the idea that a is not 40 is important because you first find that a is 40. That means it's on the same proportion, which means that they're actually the same exact line. And that doesn't mean there's no solution. That means there's infinite solutions. So infinite solutions is not what we want. Therefore, we want it to be parallel, but not infinite solutions. So we say a is not 40. Okay. Any other questions? Very good questions. Thank you guys for asking. And thank you also, Archer and Ludwig, for volunteering. All right. So let me show you guys. We can do, if you need to grab some water, feel free to grab some water. We've got about like 20, 25 minutes left. So maybe take a little break, and maybe in like 2 minutes, I'm gonna just show you guys this new game that I saw. It's a silly game also, but I think you guys, you could play if you're bored with your family or your friends. You can show this game to them, and you might have even seen it before. And please hit the yes button when you're back and you are want to check out this game. We'll get started in 1 minute. Have any of you heard of this game before? Sign Wars? I hadn't heard of it. I think they just made it up. And this lesson, I was teaching my 5th graders like why, adding negatives, adding positive and negative, and multiplying two negatives, why that becomes a positive. And there's a lot of nice explanations that they give. And this game is like an exercise to practice that, but it's fun in its own right. Okay, so here's how this game works. There's 2 players. Oops. There are 2 players, a positive player and a minus player. And it goes kind of like tic-tac-toe. So each player fills in a square. Takes turn filling in a square with plus or minus. And at the end, you do some configuration like this: plus minus, plus minus, plus minus, plus. So at the end, what you can do is you count the columns and the rows, and you see how many of them end up multiplying to be positive or negative. So if you multiply this column, all the signs in this column, plus minus times plus, we know that if you do that, that's going to be a minus. Minus plus plus is also a minus. Minus plus minus is a plus. Going across the rows, you have a plus here, you have a minus here, and the last one would be a minus. So in this case, the score is you add up the total number of minuses you got, it's going to be 4 to 2. Okay, so that's how you play this game. Anyone want to volunteer? Any two players want to play? Or do you guys want to play as a class against me? Okay, let's try that out. So please message everyone when you want to make a move. So I'll take the first move. Okay, I am going to let you guys. So first, do you guys want to be? So the first response here. Do you want to be plus player or minus player? Minus. Okay, cool. Next, do you guys want to go first or second? Second. Okay, great. So I will go first. I'm going to say plus right in the middle. Left corner top is minus. Okay. I'm going to go with a plus right above it, right here. Bottom left, okay. Minus, nice. I'm going to go with a plus, let's say right here. Middle right, okay. I'm going to go with a plus, let's see, over here. Top right. All right, and then I've only got this one. All right, let's calculate these. Minus plus minus. This is going to be a plus. Plus plus plus. This one is a plus. Minus minus plus. This one is a plus. Minus plus minus. This one is a plus. Plus plus minus. This is a minus. And minus plus plus is a minus. So it looks like I got lucky here and won 4 to 2. All right. So have any of you seen this game before? Yeah, I think it's a kind of a silly. It's not much deeper than tic-tac-toe. But if you're curious to kind of work it out, I'm curious to hear any ideas. The rules are pretty simple. See if there's a strategy. Like, is it always better to play first? Is it better to be the plus or the minus? Where should you play your turn? It doesn't matter. So these are some ideas to think about. Anyone have any ideas just kind of right off the bat? Any observations about this game? Nice, I'm getting some good ideas. Maybe plus is an advantage. That could be. To be honest, I'm not sure. Actually, it's not entirely obvious. Like, what's the best strategy? Tic-tac-toe. There's some strategies. Like, if you think about it for a little while, you can come up with some good strategies. It's interesting. So once we mentioned, if you're negative, you would try to avoid getting two negatives in the same row, because then they could just put a plus there. But sometimes getting negatives in the row could set you up for the columns. So it's an interesting game. For homework, what I want you guys to do, obviously you don't have to turn this in, but for homework, show this game and play it once or twice with a friend or somebody in your family. All right, and then see if you guys come up with, or if you play and see, get competitive, see who wins more often, plus or minus, or who goes first, or stuff like that. It's fun to explore these things. Okay, let me just finish. We'll do one more example similar to the problems that we did today. And then tomorrow we will do more word problem type stuff. So let's continue. And I just want to do one similar problem like this. Actually, you know what? I'll keep it on the same page. So just make sure you have this first example. You have it down in your notes. So so same kind of idea. Nope, that's not what I want to do. So this is a good example. This time, let's try ax plus 12y equals 8 and 18x plus by. Sorry. Okay, so please try this example. Please find constants a and b. So x and y are kind of like the variables. A and b are coefficients or constant terms. Find the right choice for a and b so that there is, instead of no solution, let's make it this time infinitely many solutions. And the numbers for a and b, if you're solving a proportion, you know that sometimes you don't get a nice number. Here they will happen to be nice numbers, but they don't have to be. They don't have to be a integer. You could get a and b to be fractions. You can solve a system if it's fractions. And later we'll do more examples like that. So please message me when you get your answer, and also message me if you're stuck, you're not sure where to start as well. Getting a few good, great responses. All right. We'll wait another minute or so. And let's maybe go over the answers here. Gabriella, would you mind sharing with us your approach, which was very good?
Yeah, sure. So for the first part, like finding, because I found an A first,
Good.
I did like the proportioning thing that you said to do.
Uh-huh.
So I did 18 over A equals 9 over 12. And then I cross multiplied and I ended up getting for A equals 24.
Exactly. Nice. And to do this without a calculator, what's something nice you can observe about like 9 over 12?
They both are divisible by 3. Like they both can be divided by 3.
Nice. So this is like 3/4. And then when you solve that out, you can cross multiply exactly. You get 4 times 18 equals 3 times a. Dividing everything by 3, you get that a is equal to. Awesome. Okay, and then Gabriel, how did you do b?
So I did the same thing, except I used 9 over 12 equals b over 28. And again, I did cross multiply and I got b equals 21.
Awesome. And then just a little bit of cross multiplying and you get the same sort of result. And again, to do these without a calculator, it's really important to simplify before you multiply. So anytime you see things that cancel, make sure you take advantage of that. For example, if you get 3/4 equals b over 28, and then multiply both sides by 28, I would do this as 28 times 3/4, and just observe that, oh, the 4 and this cancel to 7, and so this is equal to 21. And Gabriel, why do we want b to equal to 21 this time and not be not equal to 21?
I don't really know, but I'm guessing because there's infinitely, I can't say that, but there's many solutions, infinitely many solutions.
Yes. So yeah, exactly. So what does it mean for it to be, if b is 21, what does that tell us about the two equations? And everything is in the same proportion. What's really interesting about these two equations, or what do we know about that? If all the coefficients are in the same proportion, then even if it's not like a super nice proportion, the portion is like 3/4 or 4:3, whatever, however you want to set it up. When you write it in slope-intercept form, what you'll discover is that it's just the same line. They're just everything's got multiplied by a constant. So because it's the same line, they're sitting right on top of each other, and that's why you have an infinite many number of solutions. Okay, thank you, Gabrielle. That was really good. Did any of you guys have any questions about this example? There is an alternative way to solve this as well, rather than doing proportions. It's pretty much the same idea, but one trick you can do is you can try to set it up. It's just like the same concept, but just looks a little different. You can try to set it up. You see how this equation has 12y, this one has 12y, and this one has 9y? Well, you can try to find the least common multiple and multiply, try to set up an elimination, and then when you set up the elimination, you can match the coefficients. That's another good approach. So like 12 and 9, they both go into 36. So if you multiply everything by 3, so this could be multiplied times 3, times 3, times 3, and this one, the bottom one, could be multiplied by 4 times 4 times 4. Then you'll get 36y, 36y. Those are going to be the same. And therefore, 3a has to be equal to 4 times 18, and 3 times 28 has to be equal to 4 times b. So it's the same, like you get the same result at the end. I personally prefer the proportions, but if you like to like match up one pair of coefficients so that they're exactly the same, and then therefore you have like some expressions for the other coefficients, you can also do this other approach. Okay, guys, I will see you tomorrow. Please remember that assignment to play the game with, play 1 or 2 rounds of the game with a friend, even if they accuse you of being nerdy and showing them a math game. And yeah, if you have tomorrow, we will go over more of the homework assignment. I saw somebody ask me in the beginning of class about something about the homework. That was Olivia. Let me see here. On section 8.3, which questions do we need to do? just take a quick look at that one. 8.1, 8.2, 8. Yeah, tomorrow we're going to do a lot of stuff on 8.2. So if you want to prepare for tomorrow, please read that chapter section. That's going to be really helpful for tomorrow. It's going to be the focus. 8.3. Wait. Oh, sorry. Yeah, tomorrow we're going to focus on 8.2 and 8.3. I meant to say read on 8.3. 1, 3, 41, and 43. I think it was more than that, but let me just see why it doesn't seem like it's that many problems. I'm not sure. Let me look at my Google Classroom. So it looks like 8.3, I only said to do 1, 3, 5, and 7.
Yeah, but for
I don't know why.
like 7 and like the other ones, it says to go back to 8.2 or like one of the other sections and do the word problems. And I got kind of confused because we had done one of the word problems.
Oh, I see. You know what? Let's just don't worry about. So I'm gonna erase that part. If you did it, that's very good. Uh, um, I will have to look and pick some better problems from 8.3. But for tomorrow, just read over the section, look over some of the examples, because we're going to do similar examples in class. Okay. I'm just going to edit this now. I'm going to just read the section. Read the section for now. Problems will be posted tomorrow. And thank you for bringing that to my attention. Yeah, if there's ever something weird with the problems, just let me know. I didn't realize that. All right, guys, I'll see you tomorrow. Have a good rest of your day.